Thanks for the introduction. So I will present my work about effects of agglomeration on the elastic properties for nanocomposite. So and especially for nanocomposite made of PLA and CNT. So PLA is a polymer matrix and CNT are carbon nanotube. So the industry are looking for light materials that are cheap and easy to manufacture. Like this is three main characteristics that the industry are looking for. And therefore they use polymer material that regroup these three characteristics. Also, more and more we look for environmental friendly materials, which lead to the use of biosourced and biodegradable materials. Finally, they want also materials that are resistant to high loading. And to do that, we can add reinforcement to the already existing material. So, and to keep all the previous advantages of our polymers, we want to use really small fraction of reinforcement, which leads to nanocomposites with bio-based and biodegradable polymer matrix. It can be used in many sectors, whether it's automobile, aeronautic, train, or construction. Nanocomposites are made of one inclusion that has a dimension below 100 nanometers, and therefore it's lead to a high specific surface. So the surface of contact compared to its volume is really high. And at this surface of contact, an interface is formed due to the reaction between the two middle. And it's lead to a high increase in properties for low fraction of inclusion. To consider the mechanical property of nanocomposite, we need to consider multiple parameters, which are the volume fraction, shape and orientation of the inclusion, rigidity of each phase, interface, and in this case, we'll also consider agglomerates. There is some other factors that can be considered, but in this study, these are the factors that we consider. The studied nanocomposite will be polylactic acid, which is PLA, which is a biosource and biodegradable polymer, and it will carbon nanotube, so CNT will be added to it. So we'll use experimental observation. For example, here we've got a microscopic observation of so TM microscopic observation for polymers. So here we can see some free CNT and CNTs that are aggregated. We'll try to reproduce this effect with numerical study and also with an analytical model. Okay, to do that, we'll first present some of the prediction model, then we'll go to the agglomeration study and implementation of this agglomeration, and we'll see how we can also implement it in the numerical model. Okay, so first the different model. So we can use numerical model to predict mechanical properties. Numerical model are based on finite element method that use full field homogenization. So they consider the stress distribution at each point of the volume. And to do that, it's necessary to define a reference volume element, which is a RVE. So, but to define a RVE is like its stability, study of its stability is needed. So, and to do that, we need to observe the number, like the impact of the number of polarization. So how many times we repeat this study, if it's repeatable or not, and also the volume size. So how many inclusion we consider in our RVE. Furthermore, like this model, like all the model use simplification hypothesis, but it has been observed that it is consistent results for microcomposite. And the only new thing in nanocomposite is the introduction of an interface, which is considered through the geometry. So an interface is a phase that we consider in between the reinforcement and the matrix. So like a coating layer. But last inconvenience is that most of the time it requires quite long computation time. It's why we also introduce some analytical models that are much faster, but need more hypotheses in order to function. So the models that are the most commonly used in microcomposite and in nanocomposite are the mean field homogenization model. So each field is considered constant in each different phases. Using this hypothesis, it's possible to find the global stiffness of the material depending on the volume fraction of each phase, the global stiffness of each phase, and the localization tensor, so the strain localization tensor in each phase. This strain localization tensor will mostly depend on the shape of the inclusion. The most used MFH model is the one developed by Mori Tanaka, so Mori Tanaka Shem. They consider a particle and they consider its equivalent counterpart, which has the matrix stiffness, but with a free strain applied into it. And they consider that these two models are equivalent. With some elaboration of this method, they are able to find new localization tensor, so AM, and TR, like AR. So with this localization tensor, they can find the stiffness of the material, like of the composite. This model is the most used for microcomposites. It has been proved to be really efficient for microcomposites, provide really accurate prediction, and it considers the influence between the inclusion, so it can be used for high volume fraction also. But however, its drawback is like it's inaccurate to consider the representation of the interface, because there is, like, when we add the interface in this model, the interface and reinforcement are just considered as two different phases, so there is no direct link between the two, and it doesn't consider the stress transfer that happens through the interface. Another model that is widely used in nanocomposite is the double inclusion, because the double inclusion gives more consideration to the interface. To do that, it's in the hypothesis, it considers a superposition principle to take into consideration the inclusion and the interface at the same time, and not as two different phases. And some new tensor are introduced for the notation. And finally, we find the new formulation for the localization tensor. This formulation is a bit more complete. It's widely used in nanocomposite study, and it considers the difference in shape between the two phases, so between the reinforcement and interface. However, it's still unable to properly consider the interface, and in the case where the shape of the two phases are identical, it's equivalent to the Mori Tanaka chain, so it's still limited. This model is still limited. In order to solve this issue, we try to consider an incremental approach. So this time we do a two-step approach. First step, we consider the reinforcement inside the interface to find an equivalent particle, and this equivalent particle is then added to the matrix to get the homogenized property of our nanocomposite. With this approach, we've got a better consideration of the interface, which presents a direct contact between the reinforcement and interface. However, it doesn't give us a direct formulation, since it's a step-by-step approach, like an incremental approach, so we don't have the direct formulation this time of the localization tensor. Finally, we compare all of this analytical model to a numerical model. Using the numerical model is obtained using Digimat and defining reference volume elements. This case is just a simple comparison for spherical particle, and we assume two different stiffness for the interface, one time with a soft interface and one time with a stiff interface. So the interface is either softer or stiffer than the matrix. For the stiff interface, all the models that were presented seems to provide pretty accurate result and pretty similar result. However, for soft interface, Mori Tanaka and double inclusion tend to overestimate the stiffness, while the incremental approach gives more accurate results really close from the numerical expectation. So Mori Tanaka, so the incremental Mori Tanaka approach will be used in the following part of this study. Okay, so now we'll go to the main part with the agglomeration. So when two particle reinforcement are really close from each other, there is only a small space between the inclusion, and the polymers encounter difficulty to properly propagate, which leads to a weakened interface. So instead of having an interface that is really strong in between our particle, here the polymers have difficulty to propagate. So there is less polymer or even void, which leads to weakened phase over there in this area. Some approach, some model have been studied by Baek and his team. For example, he provides an overlapping degree, and from that he computes the new interface modulus. However, it's difficult to determine this overlapping degree from the experimental results, and this model is purely empirical. So we'll try to see if it's possible to find a new parameters that we can directly link to the experimental observations that we got. So to do that, we use literature data and the data from our experimental results of our team. So we use PLA and CNT. So for the PLA, we found the modulus given there of 3.22 gigapascal. And for the CNT, it was a bit more difficult. So we use literature data. We start from graphene, which is around 1 terapascal for the modulus. And CNT is mostly constituted of one graphene layer in circle, but with void in the middle. So considering this approach, we can find a longitudinal and transversal modulus of 88 and 45. But a study from Kim and its team proves that there is always default in most of the time there is default in the CNT or graphene. So the modulus is closer from 35 gigapascal. So from using this 35 gigapascal, we try to variate the aspect ratio, so the shape, the length of our CNT particle and the transversal modulus. No small difference were observed, no big difference were observed, like the longitudinal modulus is the most important factor. And for the following part of the study, we choose a longitudinal modulus of 45 gigapascal, a smaller transversal modulus, and aspect ratio of 30, which is closer from what we observe experimentally. Okay, so then we try to define the interface. The issue with the interface is that it's really difficult to determine it directly. So we just take the data from the literature and try to determine it indirectly. So in the literature, the modulus of the interface is in between 0.5 to 5 times the one of the matrix for this kind of material. And this thickness is between 5 to 15 nanometers. So we test some of the value in this range, and we observe that both parameters yield a pretty important effect on the modulus. And none of the case were able to correctly predict the experimental results in dashed line over there. Nonetheless, we choose modulus like the case of a stiff interface, and we assume that the difference between our case and the experimental data is that we did not consider the agglomeration. So we'll try to consider the agglomeration to see if we get results closer from the experimental data. For the agglomeration, we use transmission electronic microscope imagery. So from this observation, we analyze the data, and we find two main parameters that we'll use for this study. First, we select that the really smallest particles that were measured were only noise, so we neglect them. Then particles that were between 0.002 micrometers and 0.2 micrometers were considered as free particles. And finally, the particles that were bigger than this one were considered as agglomerate, because it's pretty difficult to determine all the agglomerates from just the image, microscopic image. So we determine this parameter to differentiate the free and agglomerate particle. So from that, we determine an agglomeration ratio compared to the total ratio of particle. So total number of particles, and we find an agglomeration ratio. And we also compute the specific particle density, which is the particle density, so the number of particles over the total surface, and divided by the volume fraction. So the specific particle density should be constant along all of the volume fractions studied if there is no agglomeration. So first, if we use the agglomerations that were observed for the study, and we introduce, we link to them a softer interface. So we assume our stiff interface defined before, and for the agglomerate observation, we assume that all the particles in this agglomeration present a softer interface. But doing so, we get a result closer from the expected result, but we still don't have the proper tendency. So it's a bit closer from the expected result, but we don't have the erratic tendency of the experimental test. So we try to introduce another small aggregate parameters. So because we assume, from the observation, we observed that the standard inclusion size was much smaller than the one we use to differentiate the free particle from the agglomerate. So we assume that in between, among the free particles that we consider, there was some small agglomeration, and we assume that a small agglomeration is in average three inclusion together. So from this, we were able to extract a new aggregate parameters for small aggregate, and using this aggregate for softer interface, we were able to find a more specific, a better tendency. But this approach seems not really consistent. So afterward, we prefer to use the specific particle density. So with this particle size, so with the standard inclusion size, we were able to determine the perfect particle density in the case where all the particles were perfectly dispersed. And using this theoretical density, we compare with the density obtained for each of our inclusion, and we extract from that agglomeration factor, agglomeration percentage. And with this agglomeration percentage, we once again assume that all these particles were in agglomerates, and we link them to softer interface. And doing that, we are able to fit the erratic evolution of the modulus with very accurate value when we take a value of 0.12 times the one of the modulus for the Young modulus, as we've seen on this figure. So now that we were able to extract an agglomeration ratio that seems to provide accurate results by supposing softer interface, we will implement it in our numerical model also. So the numerical model, we need to define the reference volume elements, and we want a volume big enough so the length of the inclusion is not close to 1, because in this case it will be more similar to a continuous fiber model, which is not our case, and it will overestimate the stiffness. But to avoid this issue, we need to increase the size of the reference volume. But if we do that, it necessitates more calculation time, more computation time, and it might be limited on this software. Furthermore, we study the aspect ratio. So by studying the aspect ratio, so the ratio between the length and diameter of the particle, we've seen that between 300 and 10, there were no big difference linked to the aspect ratio, but smaller to 10, there is some big difference. So we assume that with an aspect ratio of 30, the computation time was really long, and we were not able to consider a big enough reference volume to get stable results. So we assume that we go to a new aspect ratio of 10 that present pretty much similar results, but allow us to consider more particles, so to get more stable results. Also, we did a comparison for the size, so how many particles were needed to consider. And with this study, so of the evolution of the Young modulus depending on the number of particles, and also the standard deviation, because we repeat, like for each volume, we repeat 4 times the volume to see if it's stable in between each repetition. So from this study, we find that the results tend to stabilize around 17 inclusion and above. And also for the different type of mesh, whether we choose quadratic or non-quadratic mesh, there were no big difference, and non-quadratic allow for lower computation costs. So it's possible to study a larger volume with non-quadratic mesh. So we'll use, for the following part of the study, we use non-quadratic mesh with 40 inclusion to get stable results that are not too time consuming. Finally, it's another study between for the number of meshing that is necessary. This is the number of mesh in the thickness, in the interface thickness. We see that if we increase, if we select more mesh, our result will be different, and it will stabilize at one point. But it's always the same thing. If we increase the number of mesh, it will increase the the computation time. So we choose 2 mesh for the interface thickness and still non-quadratic elements, because there is still a small gap between quadratic and non-quadratic, but it's not so big, and it's pretty much constant in all of our observation. So lastly, we were able to implement our agglomeration into our numerical model, and we can compare it with the analytical model. So the numerical model is slightly underestimating the analytical model, but we still find the same tendencies that was observed before. Unfortunately, we are not able to compute the numerical model for 2% of weight fraction of carbon of CNT, because it was not possible to implement that many CNT into our model without collision between the particles. But in the end, we were able to find similar tendency between analytical and numerical models that fit the tendency observed on the experimental result. So yeah, the modulus evolution trend is preserved and fits the experimental data. So to conclude, we studied nanocomposites. So one dimension should be below 100 nanometers for the reinforcement, which lead to high specific surface and to the presence of an interface, allowing a high increase in property for low fraction of inclusion. To predict the mechanical property of this model, we needed to consider multiple parameters, whether volume fraction, shape, stiffness. And mostly in this study, we focus on the consideration of the interface and of the agglomerates. For the comparison, we use PLA CNT nanocomposites, and we try to take into account the agglomeration using the microscopic images and the specific particle density parameters that were extracted from this observation. At the end, we managed to find a suitable trend fitting the erratic experimental evolution of the modulus, and a similar trend is obtained with both analytical and numerical results. Thank you for your attention.